Okay, so hey, hi Divanshu. Yeah, yeah. Hey, hi everyone. Yeah, I hope I'm audible to everyone now. Hi Shivangab, hi Sangeep. Am I audible now? Okay, perfect. So, uh, Shivangab and Sangeep, please join the Google Meet session also because there you can ask your questions and interrupt me for any kind of confusion which you might have. Okay, so now I'm sharing the screen on YouTube Live. I hope you can see my screen on YouTube Live as well. Okay. I think Sandeep has joined on Google Meet as well. Srivangab, if you want, you can join the Google Meet link also, so that you can ask any questions which you might have. Okay, so now I will try to start with the agenda of today's meeting, which is around Gaussian algorithm. Hello, hi, Lisa. Okay, so just for everyone's information, we are on YouTube Live, so you can hear me over there, and you can ask any question on Google Meet. Okay, so today we are going to cover Gaussian algorithm from very beginning, and in this we are covering Gaussian algorithm from very beginning. And yeah, I was also wondering from where my voice came back. Okay, thank you, Praneet, for muting. I'm just confirming everyone was mute. Perfect. Okay, so before we start with Gaussian algorithm, I would like to cover few things which are very important for Gaussian algorithm or any algorithm of quantum computing, which is how does any particular algorithm is written in a in a quantum computing world. So first of all, the first step which we all have to remember is we will put our cubics in superposition usually, okay, to start with. That's one thing. Secondly, then we will do any kind of calculations. When I say calculations, these are unitary operations actually, okay, done on that superposition cubics, right? And then eventually you will do the measurements for your results, okay? Now, this is the overall architecture of any algorithm, and this is not very specific to Gaussian, Shaw's algorithm, or any particular algorithm. Okay. Now, to start with, I will tell you about the problem statement of Gaussian algorithm. What is the problem statement we are trying to solve? And then we will take a very different approach of how do we reach to the circuit. So we will not be talking about the circuit right away in this session. We will be focusing on how how did we arrive on the circuit, so that in future if we have to create our own circuit, how can we approach that? That's the main agenda of this meeting. We might not be able to cover it in 1 hour, maybe, but let's aim to cover as much as possible. And I request everyone to keep it interactive. Interrupt me anywhere if I'm going too fast or too slow, and if you have any questions on top of it. Okay. So first of all, we have to remember the problem statement of Gaussian algorithm. See, Gaussian algorithm is simply going to tell a very basic solution of figuring out the type of function. Either it's a constant function or it's a balanced function. Now, what does constant function mean? What does balanced function mean? Is what I'm going to explain now. Okay. Now imagine you have let's say two stakes, 0 and 1. Okay. And there's a function operating. So if you give an input of 0, imagine, okay, then the function will give you the output of 1. So in this case, the input was 0 and the output was 1. Okay. Now, the second case is where the same function is given an input of 1 and it gave us the output as 1. Okay. So in this case, both inputs are giving me the same output. Okay, which is 1. We call this function as constant function. Okay. Now there may be another case of constant function where 0 and 1 are inputs again, and the output may be 0 this time. Okay. So in this case, again function operated, and this may be a different function, right? This is not the same one. So let's call it, this was function 1, this was function 1, right? This was function 2, this was function 2. And in this case, the output was 0. Okay. Again, it's a constant function. It's a type of constant function because no matter what input you gave, the output was constant only. It was same. That's why it's a constant function. But there is another type of function which we can define as balanced function. Now, this balanced function is something of this sort. Let me just explain. So, imagine you have inputs of 0 and 1, and this time, let's say, keep 0 and 1 over here. Okay. Now, imagine you have given an input of 0, but the output was 1. Okay. But you have given an input of 1 and the output was 0. Okay. Which means, let's say we can call it this function as function 3 maybe. Which means that if the input is changed, right, the output also got changed. In terms of mathematics, we can also say that F3, the input was given as 0, but the output was not equals to F3 of 1. Okay. Whereas in terms of mathematics, the constant functions can be written something like that. F1 of 0 input was equal to F1 of 1, right? Now I will take a pause over here and open for any questions you guys may have uh, till now, and you can ask your questions on Google Meet because on YouTube Live I may not be able to hear your voice. And I do understand there is some lag on YouTube Live, so I will take 1 minute pause over here for listening to your questions. Okay, I think there is no question. Praneek has confirmed that. Thank you for confirming, Praneek. Now I will move forward with one more possibility of balanced function. So let's write it down. So the balanced function is one more way possible by simply having this possible states. So imagine you have 0, 1, and you have 0, 1 again. But this time, if you gave input as 0, the output will be 0. And you give input as 1, the output will be 1. Now, if you think logically, again, let's call it as function 4. So logically, again, on the change of input, the output is getting changed, which means that the function 4 input with 0 is not equals to function 4 with input of 1, because the output is not same, the values are not same. That's what we call balanced function. Now, by this point, I'm assuming that the question or the prompt statement is pretty clear to all of us. Now, in such cases, we have one wonderful way of representing this problem statement and the way function works in the way of matrices. Now, how can we do in terms of matrices is something I'm going to explain now. For that case, I will have to, sorry, my bad. I will have to take one of the possible, function. So I will take, for example, this function 3 for our reference. So let me just, yeah. So let's say we have this particular F3, okay, and the input is given as X and the output is given as Fx. When I say this simply means that I can represent it via some matrix solving. So x may be 0 and x may be 1. I mean, let's talk about quantum. Oh, sorry, my bad. Let's talk about classical computers at this point. So in classical computing, this holds true when x may have the values of 0 and 1, right? And of course, it may have the output values in 0 and 1. It may have, depending on the nature of F3. Now, how do I explain all that is by simply a matrix representation. But for that, you again have to recall the mapping of input and output. So imagine you have 0, 1, and 0, 1 again. Now, if you have given input as 0, right, then you will get an output of 1. You give input as 1, then you will get an output of 0. Okay. So, in this case, what you can do is you can represent this particular basic classical circuit using a matrix. For that, you will have to think in terms of input and output possibilities. Now, think about having a 2 by 2 matrix over here, okay, where your 0 and 1 are the input states and 0 and 1 are the output states or the output values, okay. So if you think here, right, when the input was 0, the output was 1, which means this value was true. So when the input was 0, the output was 1, right? But when the input was 1, Okay, the output was 0, which means that when the input was 1, the output was 0, which means this one. Okay, so this matrix, and of course the rest of the values are 0. So this matrix is basically representing the functionality of this function tree. So in nutshell, in terms of matrix, I can represent this using this matrix. Okay. Now, how do we validate that whether it's working fine or not? Okay, we can simply do it. That's what we learned in the previous sessions. How can we do it? So in this circuit, if you see carefully, right, if this function tree, okay, is operated on 0, right? So this will return me 1 as an output. In terms of matrix, how can we represent it? We can simply say that F3 is operating on cat 0, right? And let's say we don't know what's the output value. We don't know it. So let's calculate it. So F3 is nothing but the same matrix which we have 0, 1, 1, 0. Okay. And how do we represent this particular cat 0? It's 1, 0. Okay. Now, if you just multiply it, you will get 0 and 1. Yeah. Which is nothing but cat 1. And that's what was actually happening in the, you know, in the actual prompt statement, because this is one of the balanced function. Okay. Now, by this point, you know, our classical part of the problem is done. Uh, I will take again a pause of 2 minutes and open up for questions or suggestions or anything which you want to confirm before I move on to the quantum part of it. So I'm just waiting on the Google Meet link. Okay. So if there is no question, I'm just moving forward with the quantum part of it. Now, while moving to the quantum part, you have to realize that you can write similar matrix for F1, F2, F4 as well, the matrix which we have written, right? We can write it for, um, you know, other functions as well in the classical world. But in the quantum world, okay, we have to write our circuit in a way that it is always and always reversible or unitary. Okay, that's what we have to ensure every time. So for this, what we have to do is we have to define, you know, this as an oracle function, so that if it is applied one more time to the same output, you will get the input back. Now, it may sound a bit complicated to hear for the first time what I'm saying, but you will understand it more clearly once I draw the circuit for that. So, what I'm trying to do basically over here is I'm trying to represent this particular function, right, with, let's say, cat, x with fx as an output. I'm trying to transform this circuit to a quantum circuit, right? Why? Because at this point, if you think carefully, this circuit is not reversible, which means by checking the value of output, you cannot predict the value of input at all. There's no way you can do it. Okay. But in quantum, you have to, design your circuit in a way or gates in a way that they are reversible actually. And we have discussed a lot about it in the previous sessions as well. So for that purpose, we will go with a circuit like below circuit which I'm going to draw, which will have not just one input, it will have two inputs. And one input will work as a control bit or control qubit, I would say. Okay. So let's see what I'm talking about. So if you look at this particular UF, right? And we sometimes call it Oracle as well. So it may be UF or UF3, whatever you can call it. Okay. But this is a generic circuit for, any kind of a function you may have in classical world. In this, you will have input as cat x and cat y, but the output will be something like this. And we all know what is y with XOR fx is. Okay. Now the benefit of this is that by looking at the output state, right, you can always predict or get an knowledge of the input state as well, which was not possible in the classical computing. Now, when I say it, I mean we have a truth table which can be represented for this particular case. Now, let's look at the truth table very carefully about it. So, let's say we design a truth table for x, y, which are of course input, right? And then we define, so this is x, y, and the output is again x, and the second qubit is y plus fx. Okay, let's design a cube, let's say truth table for this. Now, of course, you can have possible values of 0, 0, 0, 1, 1, 0, and 1, 1 over here, right? In this case, of course, the output of this one will remain same as the input of x, so it will remain same. But this is where the things will get interesting. Okay, so what is the value of y plus fx for this particular combination? So if you think carefully, right, y is 0 in this case, right, and fx, right, is dependent on the function, which is f3 in this case. Now I will just move my screen bit towards this direction for helping you on that. So if we are talking about the f3, right, if you remember that, so when our input was, you know, when our input was uh, 0, okay, so the output was 1 in that case. Am I right? And in the case of XOR gate, whenever the input is different, whenever any of the input is different, right, you get a value of 1. So this is the value you get for this one. Now, same thing you can do over here. In this case, 1 plus fx, right? And similarly, you can operate, 1 XOR with 1. And whenever the inputs are same, right, XOR gate will give us the value of 0. Similarly, you can keep on doing for the rest of the, values. Now, the idea which I'm trying to present over here is that this is a generic formula, and if it is combined with this x, this becomes a unique combination, actually. So if you think carefully, this is nothing but fx. So this 0 was not playing any role over here, right? And it was simply coming as fx. Whereas this was the 1 XOR with fx. So when you look at this combination, when you look at this particular combination, you can figure out your input as well in this case. And this is true for all the combinations. So if you do further mathematics, you will again get, uh, this. So by looking at combination of 1 with fx, 1 with 1 plus fx, this is a unique combination and you will get unique combination of x and y over here in the input. So I will again take a pause over here and open up for any questions which you guys may have for this. By the way, am I audible? Okay, I think there is no question. Okay, thank you, Rajesh, for confirming that I'm audible. Okay, now moving forward, I will talk about the reversibility of the circuit. Okay, how do we confirm that? Now, if you just go up and draw the same circuit, right, same oracle, and you apply to the output of, I think my pan is having some issue. Yeah, yeah. So if you apply this cat x, cat y, right, of course you will get the output as cat x, cat y, XOR with fx. But if you again apply this oracle, okay, typically you should get, the input state back in the output. That's the whole purpose of reversible gates or reversible operations. right? Now, how do we confirm that? So, if you look at the equation, right? So, in this case, what should be the output at this pin? So, let's think about it very carefully. So, the output at this point should be something like cat of y, right, with particular fx, okay, which was this one, right? And then again doing an XOR, okay, of this one. So let's keep it in a bracket. And again doing an XOR with the function of x. That should be the output at this pin, okay? Now, if you do the mathematics again on this part, you will see that this is this is simply the associative property of XOR gate. So you can write it something like, this one. Okay. Now, as we all remember, right, whenever the inputs are same on the XOR gate, we get the output as 0 in the XOR gate. Okay. Which means that this thing becomes 0 over here. Okay. And we again remember that in XOR gate, whenever any input is 0, right, it simply passes on the rest of the operation. So this will get, ignored, or I would say this will simply pass on the y. So if y will be 1, it will pass on 1. If y will be 0, it will pass on 0. So the effect of 0 goes nullified over here. Okay. So it will become xy. So hence we have seen that if you have reversed or if you have applied the same rate again over here, you will get the output as same one. Now, the purpose of doing all that mathematics was that, like the way we have written this circuit, in the way the matrix has been written for classical world, we have to write a quantum matrix for this particular circuit. Okay. So when I say quantum matrix, it means it will have 4 by 4 matrix, which will give me the combination of inputs as well as combination of output for this particular function 3. Now, what do I mean by that? So, if you can carefully, let me just read off for you. So, I am again talking about the UF3, which is the third right function. We can do the same logic for F1, F2, and F4 as well. Now, again, you have input as X, Y, and you have X coming out, Y plus Fx coming out, right? Now, as we can see, we have two inputs, right, over here. And of course, the matrix, right, will have inputs as 0, 0, 0, 1, 1, 0, 1, 1, okay? And of course, it may have output as, because again, the output you have two, two qubits. So you may have output as 0, 0, 0, 1, 1, 0, 1, 1. Okay, so these are the possible outputs you may have. Now, for the input 0 and 0, what will be the output in this case, right? We have already calculated it in the above truth table. So if you notice, in the case of 0 and 0 as an input, right? First of all, this will remain same. So this will be 0 for sure, which means the answer may be among these two, because in this x is 0. X is here 0 and here 0. So it may be here or here, anywhere here, right? Now, which one among these you will just calculate this one, okay? So for 0, 0, the value will come as 0, 1, and we have already done that. If you notice, in the truth table, if I go up, right, we have done that. So if you see, in this case, the value was coming as 1, which is the output. The second qubit was coming as 1, and the input qubit was 0. So the 0, 1 is the output in this case, right? Sorry. So I'm just again going back to the circuit. So in this case, this will be the, so for this input, this will be the output, right? And of course, the rest of the things will remain 0, 0, right? By doing the similar, mathematics for the input 0, 1, you can figure out that the output will become something like this. And again, you will keep on doing. I have already made a note of it, so I remember that, but let me just write it for you guys. And that's the most wonderful part in this, in this circuit, that you will have to write this matrix, right? Not for F3 only, right? You will have to write this matrix for F1, F2, and F4 also, right? Why? Because, just doing a quick recap, because F1 is something where, you know, 0 and 1 were coming as 1, right? Maybe F2 was something, I forgot what was F2, but let's say F2 was 0 and 1 was coming as 0 as an output. And F4 was, let's say, 0 and 1 and 0 and 1, right? Like that. So this matrix will be different for each and every, function. So this matrix will have different values. So when I was studying this topic, I calculated this matrix for all possible, functions f1, f2, f3, f4. So basically, what we are doing, we are writing the quantum counterpart for the classical, circuit. That's what we are doing. And of course, it has more pins, more input pins, more output pins in this case. Now I will again take a pause on this matrix and open up for questions or doubts you may have, because this is very crucial to understand Doshe. Because by this point, uh, you know, Doshe will be almost 50% finished. Then comes the circuit designing part, which is very interesting part, of course, but it is not possible to do that part if the matrix is not understood properly. Like how this matrix came and how is it related to function 1, 2, 3, and 4. Now I will take a pause. I will just go on mute for a moment and open for. Okay, so just to recap, the question asked by Rajesh was, uh, can we have more than two bits? I would not say even qubits, more than two bits or two or more than bits, right? In Gaussian algorithm. Answer is, the simple answer is no, because that is not the scope of Gaussian algorithm. Because Gaussian algorithm is only meant for one qubit actually, or one bit. Okay, so if I'm just recapping for you. So the prompt statement was that if you have given any arbitrary bit over here and you are given a black box function, right? And just operates on that bit. So you just have to identify whether it's a constant function or it is a balanced function. Okay. But the scope of Gaussian algorithm is restricted for one bit only. Okay. For uh, multiple bits, you will have to go to the next algorithm, which is Gaussian-Schroeder algorithm. In that, we will cover about the multiple bits. That how can we identify whether a function is a constant function or balanced function for multiple bits if the multiple inputs are there. But Gaussian is only for one bit. Of course, the quantum counterpart is having one more bit, okay, to make it reversible circuit. But that's a control bit. It's not an input bit actually. You have to remember that thing very carefully. And it's not an input bit. The input is only one. So I hope I answered your question, Rajesh. Okay, welcome. I think there's one more question somewhere on the chat. Okay, I think this has to drop off. Okay, great. So I think we wanted to restrict this session only for 1 hour to respect time of everyone. Um, we will cover the rest of the part tomorrow around the same time, uh, in which we will focus on the circuit designing part for this particular Gaussian algorithm. So by this point, we have covered that how we can represent the problem statement in quantum world. So what is the quantum world counterpart of the classical problem? That's what we have covered, and also we have covered the mathematics behind it. The matrices behind it, the truth table behind it. We have covered that in this particular case. I know we went into very much detail, but that was necessary for putting up the fundamental blocks of understanding the first algorithm which we have. So we are just finishing on time. I'm just stopping my screen share and I will be stopping the YouTube live streaming as well.